Okay, let's dive into this. Have you ever looked at a complex mathematics exam paper and felt like you were staring at a chaotic night sky, just completely filled with random points of light, floating numbers, and absolutely no clear direction? Look, navigating the Cambridge mathematics exams, whether you are sitting the notorious 0580 syllabus, the 0606, 4024, 4037, or the 4040, is exactly like charting the stars. It requires a rigid structure, a rock-solid strategy, and most importantly, it requires you to decode the mathematical models hidden within the command words. Welcome to this masterclass explainer. Today, I'm your strategist. We are not just going to memorize formulas like a textbook, we are going to become astronomers of mathematics. Let me paint a picture for you. Picture two students, Alex and Sam. Alex is the overloader. Alex memorizes every single raw mathematical fact, every equation, but applies zero analysis. On the other hand, we have Sam. Sam rushes. Sam completely misses the command word requirements, ignores the context, and just starts mashing numbers into a calculator. If we look at a dynamic split screen of their typical answers, it's just a sea of red pen marks. Why? Because they don't have a system. Today, we're going to transform those red marks into green check marks. We're going to look at seemingly complex data, find the constellations, and chart your course straight to top marks. Here is our masterclass roadmap for this explainer. This is exactly how we are going to build your mathematical success blueprint today. First up, we'll tackle real-world trigonometry modeling. Then we move into visualizing trigonometric graphs. From there, we are going to absolutely conquer spatial geometry before we take on the 3D exam challenge. And finally, we'll wrap the whole thing up with advanced trigonometric equations. We are covering the exact assessment objectives the examiners are hunting for. So let's jump right into Section 1, Real-World Trigonometry Modeling. This is where we introduce the first major hurdle of the ascending difficulty arc, translating daunting real-world scenarios into workable mathematical models. We are going to strip away the real-world context to find the pure mathematical skeleton underneath. Imagine you are sitting in that dead silent exam hall. The clock is ticking. You flip the page and you find this exact scenario from a past assessment. We need to model a ride on the London Eye Ferris wheel in central London. Close your eyes for a second and really visualize it. The problem gives us a huge pile of raw data. The wheel has a massive radius of 60 meters. Its lowest point, where the family actually steps onto the ride, is 15 meters above the ground. And the wheel takes exactly 30 minutes to complete one full sweeping revolution. Now, this is where Sam completely falls apart. Sam sees 60 meters, sees 15 meters, and just blindly starts multiplying them together because Sam is rushing. But a true exam strategist steps back. We are talking about a circle, right? We're talking about continuous rotation, and we're talking about height changing over time. This absolutely screams periodic function. It is textbook trigonometry. But to solve it, we need to introduce the Peel framework, adapted for mathematics. Point, evidence, explanation, link. Top students use this to structure every single answer. So the crucial point is, the exam board actually hands you the key to the castle if you know how to turn it. The assessment provides the specific mathematical model. They tell us that the height of the family above the ground, let's call it h in meters, at t minutes after entering the wheel can be modeled by the formula h equals 15, open bracket, 5 minus 4 times the cosine of 12t degrees, close bracket. Look at that equation. I know, it looks terrifying. Alex would look at this and freeze, trying to memorize it. But the secret to exam strategy, your point in the PEL framework, is realizing that this equation is simply a machine. You feed it a time, t, and it spits out a height, h. You don't need to reinvent the wheel, you just need to operate the machine correctly by following the command words. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, back to the model. Your evidence is the specific time you are asked to evaluate. Let's see how we process this step by step. Let's put this machine to the test with a direct 3-mark question from the paper. Calculate the height of the family after exactly 10 minutes. This is our explanation phase of the Peel framework. We do this live, step by step. Step 1, we take our given time, t equals 10, and we carefully, methodically substitute it into our model. The tricky part is inside that cosine function. We have 12 times t. So 12 times 10 gives us 120 degrees. Step 2. We need to calculate the value of the cosine of 120 degrees. Now, if you know your unit circle, and you absolutely should, you know that 120 degrees sits squarely in the second quadrant, where cosine is always negative. Specifically, the cosine of 120 degrees is negative 0.5. Step 3. We plug this back into the rest of the equation. We we have 5 minus 4 times negative 0.5, while negative 4 times negative 0.5 is a positive 2. So the bracket simplifies beautifully to 5 plus 2, which is 7. Finally, we multiply that 7 by the 15 hanging out on the outside of the bracket. And boom, 105. That is our link back to the real world. After exactly 10 minutes on the ride, the family is suspended precisely 105 meters in the air. By methodically trusting the model, decoding the command words, and working through the Peel framework step by step, we've secured full marks on what looked like an impossible question. Alex and Sam would have dropped all 3 marks here, but not you. You've just turned red ink into green check marks. Let's keep this momentum going. Section 2, visualizing trigonometric graphs. We are going to smoothly transition from algebraic equations to visually understanding cyclical behavior. This is where we separate the top-tier students from the rest of the pack.
And this brilliantly illustrates exactly what I mean. This output from an ICT graphing activity shows the classic, perfectly symmetrical wave of the sine function, y equals sine x, plotted from 0 degrees all the way up to 360 degrees. Notice the journey it takes. I want you to really trace it in your mind. It starts at 0, climbs to a peak at 90 degrees, smoothly descends back through the horizontal axis at 180 degrees, plunges down to a trough at 270 degrees, and rises back to complete its cycle at 360. Alex tries to memorize every single coordinate on this line, but that's incredibly inefficient. This visual isn't just a pretty picture, it is the ultimate cheat sheet for solving complex equations if you understand its symmetry.
Let's pose a critical exam question right now to prompt some active thinking. This is where Sam notoriously drops marks because Sam just punches numbers into a calculator and immediately moves on. The assessment asks, referring to the graph, explain why the equation sine x equals 0.7 has 2 distinct solutions between 0 and 360 degrees. If you type inverse sine of 0.7 into your calculator right now, it's only going to give you one single answer, roughly 44.4 degrees. But the command word is explain. The Cambridge examiners want you to show them that you understand the whole picture. How do horizontal intersections actually work on a continuous wave? The absolute core logic behind the 2 solutions relies entirely on the symmetry of the wave. Think about drawing a straight, horizontal line across that graph at the height of y equals 0.7. Because the sine wave starts at 0, climbs up to a peak of 1 at 90 degrees, and then symmetrically falls back down to 0 at 180 degrees, that imaginary horizontal line at 0.7 is going to literally slice through the wave twice. It hits it once on the ascent, that is your calculator answer of 44.4 degrees. But it hits it again on the descent, perfectly mirrored on the other side of the peak. To find that second solution, you use the fundamental symmetry of the shape. 180 minus 44.4 gives you 135.6 degrees. By visualizing the shape, you completely unlock the second mark. It's a massive transformation in how you approach the paper. Stop scrolling, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, you're subscribed, you're focused, let's level up. Section 3, conquering spatial geometry. We are moving away from the abstract graphs and stepping back into the physical world to create accurate mental pictures of the problem. This is where we kick off our interactive workshop. I need you completely dialed in for this. Before we solve anything, we need to strictly define the vocabulary. These are vital exam terms. Angle of elevation. This is the angle measured upwards from the horizontal line of sight to an object. Imagine looking straight ahead, then tilting your head up to look at a treetop. That upward tilt is your angle of elevation. Conversely, the angle of depression, the angle measured downwards from the horizontal to an object. Imagine standing on a cliff, looking straight out at the horizon, and then tilting your head down to look at a boat at sea. Both of these are always measured from a horizontal line. Forgetting to draw that imaginary horizontal line is the #1 reason students fail these questions. Okay, challenge 1, data scan. I'm putting 60 seconds on our virtual clock. Look at the next set of data and try to extract the core trend before I reveal it. Ready? Go. Let's compare these 2 specific challenges from the assessment. In column 1, we have the 2 trees problem. We're told 2 trees stand 16 meters apart. The tops of these trees make an angle of theta degrees at a single point A on the ground between them. One tree is 5 meters tall, the other is 7.5 meters tall. In column 2, the 2 hawks problem. Hawk Q is flying 250 meters vertically, directly above Hawk P. They both spot a snake at point R, which is 2.8 kilometers away. Notice the unit change? 2.8 kilometers is 2,800 meters. Time's up. Did you spot the trend? Here's challenge 2. Find the flaw. Listen to this flawed paragraph from our friend Sam. To solve the Hawk's problem, I draw one triangle with 250-meter height and 2.8-kilometer base, then find the hypotenuse. What's the flaw? Sam missed the unit conversion, and Sam completely missed that there are two triangles stacked on each other. The strategy for both columns is the exact same. Extract the variables, convert all units to meters, and isolate the hidden right-angle triangles. You strip away the complex story about birds and trees, and you are left with pure, solvable geometry. Let's move to and see how this builds into something even bigger. Section 4, the 3D exam challenge. We are officially ramping up the tension as we enter the most daunting realm of the syllabus, three-dimensional space. Take a deep breath. Prepare yourselves for the Great Pyramid of Giza problem. When students read this paragraph, they usually panic and skip straight to the next page. But not us. Let's lay out the raw, overwhelming facts and organize them. The pyramid has a total height of 146 meters. We have two observers, A and B, standing on the same horizontal ground, both 1.8 meters tall. The distance between A and B is 25 meters, and crucially, the angle of elevation from observer B to the absolute top of the pyramid is 12 degrees. We are told A, B, and the top of the pyramid are all in the same vertical plane. That last sentence, that is the examiner winking at you saying, don't panic, this isn't as 3D as it sounds, you can slice it down the middle into 2D. Okay, challenge 3, speed writing. You have 30 seconds to mentally outline one perfect peel paragraph on how to start this. Where's the right angle triangle? Timer starts now. Think about the horizontal line of sight. Time's up. Let's see if you hit the mark. The ultimate goal here is to find the angle of elevation theta of the top of the pyramid from person A. How do we map 3D right angle triangles onto this monument? Here is the absolute critical trap, the one that catches 80% of students. The pyramid is 146 meters from the ground, but the angle of elevation is taken from the eyes of the observers, who are 1.8 meters tall. So, your vertical height for your mathematical triangle isn't 146 meters. You literally have to subtract the observer. It's 146 minus 1.8, giving you an adjusted height of 144.2 meters. If you miss that, every single subsequent calculation is dead wrong. Once you have that true working height of 144.2 meters, you use observer B's angle of 12 degrees and the tangent function to find the horizontal distance from B to the center of the pyramid. Then, you simply add the 25-meter distance between A and B to find A's total distance from the center. Finally, use inverse tangent with A's new horizontal distance and the vertical height of 144.2 to find angle theta. It's a multi-step journey, but mapped out triangle by triangle, it is 100% conquerable. We've made it to the summit, Section 5, Advanced Trigonometric Equations. Let's reach the absolute peak of our mastery arc by diving into the final challenge, manipulating equations and transforming graphs like true mathematical architects. Now, what's really interesting about this slide is the stark contrast between the standard base function and its transformation. Our base function is f of x equals the cosine of x. We know exactly what that looks like. It starts at a peak of 1, dips down, and comes back up. But the assessment asks us to describe the exact transformation that maps that base function onto the graph of y equals cosine of, open bracket, x plus 120, close bracket. When you see a mathematical change happening inside the bracket directly with the x, it means the entire graph is shifting horizontally along the x-axis. It is a translation. But here is the counterintuitive secret you absolutely must remember for the exam. A positive number inside the bracket actually shifts the graph to the left, into the negative direction. It feels backwards, but it's true. So y equals cosine of x plus 120 is the exact same shape as the standard cosine wave, but the entire thing has been picked up and shifted 120 degrees horizontally to the left. Let's break down the logic of this specific exam trick question. This is a classic 0580 curveball. The paper asks, explain with the aid of a graph why the equation cosine x equals 3 over 2 has no solutions. Sam, our rusher, might just type inverse cosine of 1.5 into the calculator, get a big math error on the screen, and scribble down calculator says error. That scores exactly 0 marks. The command word was explain with the aid of a graph. You need the Peel framework here. Point. Identify the limits of the cosine wave. The maximum value of the basic y equals cosine x wave is strictly 1. The minimum value is strictly -1. The wave just smoothly oscillates forever between 1 and -1. Now the fraction 3 over 2 is exactly 1.5. If you draw a horizontal line at y equals 1.5, it literally sits in the sky, floating completely above the wave. The wave never physically reaches it. Because 1.5 falls completely outside the graph's possible physical range, there's absolutely no point of intersection. Therefore, mathematically and visually, there are no solutions. Prove it visually, and you guarantee the marks. And that brings us to the ultimate overarching strategy. Our mathematics success blueprint is built on 3 rules that guarantee top marks. 1, command word decoding. 2, Peel framework application. And 3, a strict time management matrix. Or simply put, visualize the shape, decode the model, and solve step by step. Remember how we started, looking at a chaotic night sky? But now you know how to find the constellations. You don't just see a Ferris wheel, you see a cosine function. You don't just see a massive pyramid, you see layered, right-angled triangles with a subtracted observer height. You have learned to ground abstract numbers in logical, visual steps.
So I leave you with this. Which real-world mathematical model will you decode next on your path to exam mastery? Will you tackle vectors, algebraic fractions, or perhaps statistical histograms? Listen closely, students. Who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to at Ace the Exams _IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep charting those stars, and I'll see you in the next explainer.